We want to talk about open source today and how to quantify the chances, the probability that you have flaws in those open source libraries. As you kind of go into this, how much thought do you think that your developers put into selecting open source libraries? And whether or not they actually think about security when making those choices? Right, there's shaking heads. And I always like to talk about this OWASP survey that was done about 10 years ago, where they interviewed about 200 different developers and asked them what their priorities were when they selected software, selected libraries. And here's the rankings. Number 1 was functions and features. Number 2 was performance. Number 3 was usability. Number 4 is uptime. Number 5 is maintainability. And number 6 is security. I don't know if number 6 was the last or if I just stopped writing down there because that was security. But if you think about it, is that necessarily wrong? No, not necessarily, right? The software has to work. It has to be maintained. There are a lot of things that have to be right. But you could argue that once you get that far down the list, maybe security isn't even being considered at all. We'd like to hope that it is. But as we think about this and making the assumptions that your developers are looking at security as one of the aspects here, we want to give a little bit more guidance on some of the factors to look at when you're selecting a library and what not to look at, and hopefully make this process a little bit more easy, consistent, more scientific than just like, oh, I like this one because I've heard of it, or it has a lot of commits, or my friend was using it, right? How can we make this a little bit more scientific? So let's get into it. Disclaimer, I'm going to skip that. Okay, so let me set the stage for you. And I'll preface by saying everything in this report, everything in this presentation comes from real data, from real applications. So there's no opinions here. These are all facts, and facts and numbers. So once developers, when they're building software, once they pick a library, an open source library and a version, they tend to stick with it. And we find that 79% of the time, and this is across Veracode applications that have been scanned by, customer applications that have been scanned by Veracode, they never update that library. So they choose whatever's current, hopefully as of that day, and then they forget about it forever. And that's where you end up in situations like Log4j coming out, and suddenly people are 5, 6, 7 years out of date because libraries never get updated. Even if you look at the data and you slice it where you're only looking at applications that have been getting scanned for over a year, with over 100 scans, that number only drops slightly to about 73%. So most of the time, the vast majority of time, developers are not updating libraries. And they should be, right? Most updates are small. When there's a vulnerability in a library and a patch comes out, the vast majority of the time, it's a minor or a patch release that's unlikely to introduce breaking changes. But what happens is we let those pile up, accumulate security debt, and they never get updated. And so that's kind of the world we're living in. Meanwhile, you see that third-party code is a huge amount of modern applications. Now, it varies a lot by language, but look at Java. Java is like 98% open source when you look at a typical enterprise application. It's a little bit different when you look at C++ or PHP, where there's like a lot less shared code, but you can see that it is a big percentage of these languages that we see a lot in enterprise applications, .NET, JavaScript, Java. Over on the right-hand side, what we're showing is the percentage of flawed libraries by language. And so the highest number there is actually in the upper right with Java, and about 7% of flawed libraries in Java are flawed. But also notice that there's a pretty wide variance, with the line being the median, but you've got a lot of dots up to the 50% point, so there's a pretty wide variance there. We'll talk a little bit later about the OpenSSF scoring methodology, and one of the metrics they look at is vulnerabilities. But the thing to point out here is this is as viewed through real-world applications being scanned by enterprises and customers. So that's just to sort of kind of set the stage. Now, as we think about open source risks, This is a OWASP list. It's a very early OWASP list. I think it's a version 0.1 that was just released a little while ago. But going through and preparing for this talk and thinking about, well, what are all the vulnerabilities, all the risks in open source, the list that we came up with kind of manually overlapped almost perfectly with this list. So I thought, okay, well, let's use the OWASP list. Now let's whittle it down a little bit. If we look at the things that are grayed out, let's talk about what those ones are. So compromise of a legitimate package, that can happen for a number of different reasons, right? There's sort of externalities to the code. Name confusion attacks are completely outside the package itself. It's kind of assuming that somebody might type the wrong name in for a library and then get something that's malicious. Unapproved changes is kind of a subset of the compromise of a legitimate package. So those three are all about attackers getting their own code running in the package that you assume to be trusted. And then on the number 7 there, license risk, also not exactly a security risk, kind of a standalone thing, whether the license is friendly or not, but not really related to, is this library safe to use from a security perspective? So we're going to cross those off. Then, if we look at these ones that are highlighted in yellow, it may not look yellow to you, but just bear with us. All of the yellow ones are actually pointing back to known vulnerabilities. So if you think about unmaintained and outdated software, that's only a problem if there's actually a vulnerability found in those packages. Untracked dependencies, only a problem if there's a vulnerability found. The immature software, may be more likely to have vulnerabilities, but again, it comes back to this idea of vulnerabilities. And then finally, undersized and oversized dependency is about controlling attack surface. Like, don't use a massive library if you are only using it for like one function and one method, because then you've got all this extra code that may be exposed. But again, that's about controlling attack surface in case there's a vulnerability. So where that leaves us is we should focus on known vulnerabilities. And that's where we actually end up addressing the majority of the risks, right, that are on that list in some form. They're all kind of variations of that if we eliminate those things that involve like an attacker directly targeting a project through other means. So that's kind of where our focus will be.
And as you may notice, some of these other ones, so like outdated software, as Chris said, that might be an indicator of vulnerabilities in the future. So if something is outdated or unmaintained or immature, or there's other attributes, and this is what we're going to look at later in the talk, those all may be able to help us understand if we're going to expect vulnerabilities, and that's where we're going to head to.
So let me give you a sense of the different data sets that are in this report. And there are a few, and we'll try to kind of call back to where the data is coming from as we go through some of these charts. But number one, we have data that comes from Veracode customers scanning their applications. That's data set 1. So real world, I'm just going to call them enterprise applications, even though it kind of comprises small, medium, and large organizations. I'm just going to kind of call that enterprise apps. A lot of different verticals, a lot of different languages, hundreds of thousands of applications in that data set. And you can kind of see the number of software composition scans and findings in that data set. Then there's another data set looking at just sort of GitHub itself and the metadata around the projects in GitHub. So you can see examples there: user or organization, when was the last update, commit diversity, which we'll get into a little bit later. And then there's a third data set, which is the OpenSSF scorecard, which we'll spend a little bit of time on in just a minute. These are some various factors that are applied, that are measured in open source projects to come out with a security score. And so we'll be kind of cross-referencing and overlapping some of these different data sets and showing you how they interact with one another.
And just to put some numbers, the number of applications with SCA scans, I don't know off the top of my head. Tens of thousands? 100,000?
Hundreds of thousands.
Hundreds of thousands?
Yeah.
And then the GitHub repositories, I think we ended up scanning over 30,000, pulling all of the metadata for about 30,000. Those are 30,000 that we saw used and referenced in actual software in use in enterprises. And then the OpenSSF scorecard, they currently score, I think, 1.2 million repositories. And the next slide will talk about sort of the relationship between all of that.
Yeah, so the OpenSSF scorecard, the idea of this is to understand the security posture of an open source project so that you can assess the risks that might be introduced by them. And the way it works is it measures a number of machine checkable factors on a scale of 1 to 10. And each of these factors is weighted in terms of importance, so low, medium, or high, and then they take those weighted risk factors and then consolidate them into a numeric score between 0 and 10 that is easily digestible, I guess. If you're an open source project maintainer, there's a bunch of different tools available for calculating the OpenSSF score that they release. You can just dump it right into your CI/CD and have it calculate and report a score back to them for their database if you want to do that. Some of the examples of factors we'll look at, and we're going to dig into a few of these, and there's about 15 total. Number one, does it have unfixed vulnerabilities? Does it use a dependency update tool? Does it have a security policy? Does it have a license file? Things like that. All things that, somebody might say, oh, well, it might be more dangerous if it has this or if it doesn't have this. And that's what we're actually going to get into. Are those assumptions correct or not? Talking about the data sets again, we may refer back to this. The big circle is that 1.2 million open source libraries that are currently being scored by OpenSSF. The small circle is the real world enterprise applications scanned through Veracode. And so the interesting thing here is that only a very small percentage of that OpenSSF repository database are actually being used in real applications, right? 4%. That overlap in the big circle and the small circle is only about 48,000 applications, libraries. So that was interesting. There's all these things being produced and being scored that are actually never being used, or not being used by this range of customers anyway. So that was interesting to kind of look at. Now, when figuring out where that overlap is, it's not a perfect, it's not a science. It's not a perfect science. There are naming issues. Does the name of the library observed in the real world application match up exactly with what's in the OpenSSF repository? Sometimes yes. Sometimes there are some heuristics that try and make some matches there. But ultimately, there are probably some that did not get matched perfectly. Right. And so some of the stuff that's on the sort of the outside of the small circle might actually be a little bit on the inside, but close enough. So if I talk about big circle or small circle or the overlap on these subsequent slides, hopefully you'll know what that means.
Did you want me to jump in here, or you paused?
Go for it. Yeah, no, I was thinking, but no, jump in.
So this is looking at, as Chris said, the small circle to the big circle. The red here is the big circle, and then the blue is the overlap, right? The overlap between the two. And so this is looking at the score. And so in this case, again, 0 to 10, with 10 being good, 0 being has opportunities type of repository. We're seeing that things actually used in applications generally score higher. You can sort of see that red distribution, those lines, they sort of shift more right. Generally speaking, the scores are higher. And so it's a good thing, I think, and maybe it's reflective of a whole bunch of different things. Again, we're only looking at correlation here. There's zero causation, I think, here. But things that are used in an enterprise are probably looked at to be more mature. Maybe they're easier to integrate. Maybe they're more prevalent and seen elsewhere. Who knows why this is happening, but we do see generally a higher score in those being used in enterprises versus not.
So for whatever the reason, that's kind of good.
Yeah, that's kind of good. So this is a little bit of a crazy plot, and there's going to be a few crazy plots here, but This is 4 different variables and looking at the correlation across the OpenSSF scores. And so like the one in the upper left is looking at total contributors to a project. So if we just look at the raw number of unique groups contributing on a project, you know, we see between 1 and over 1,000 in some cases. And then the different scores that come up on the scorecards, that's what we're seeing across there. So like at the right end, we're seeing more contributors. So as you get more contributors, generally you get better the scorecard scores from OpenSSF. The bottom left, we're looking at committer diversity, which is something I'll go into a little bit later. But this is looking at basically if you have one committer doing all the commits, you have very low diversity. If you have 10 people, but still only one person does 99% of the commits, you still have low diversity. If you have 10 people and they're relatively even, you've got pretty good diversity. And even more, you can get larger and larger diversity. But you can see as that diversity goes up, as you get more committers, more people getting involved, the score does tend to go up. And so we're seeing some correlation there. In the upper right, we've got days between active development. And so this is sort of repetition. Are we seeing, you know, a lot of activity, sort of continual, consistent activity? And when we see that consistent activity, we see that going down, then we're seeing slightly higher scores as well. The last one on the lower right, days since the last commit. This was a thing that often gets talked about. Are we seeing dead projects, things like that? And we do, in fact, see pretty strong correlation here that things that have been dormant for a while generally have lower scores. Things that have been more recently active, we're seeing generally a higher score. Now that light blue part in the back is sort of given a feel for the range. So this is not, like it's not a straight line, it's not, everything is on this line. There's a lot of variation, but generally speaking, we're sort of following the red dots and the blue part in the middle. There's a lot of variation.
So if you're faced with using a library that doesn't have a score, right, doesn't have an OpenSSF score, and you can't scan it directly, looking at the commit activity, right, may offer some indication of code that's likely to be more or less secure based on kind of these charts. And the way I like to think about these charts, at least the way it makes sense to me, is that it's a sort of a box plot in motion, right, kind of left to right. And so if you imagine everyone kind of familiar with that sort of visualization, just box plot in motion, so that you can figure out what the different delineations mean.
And so this is an interesting way to look at remediation time. So this is, again, looking at the projects being scanned with SCA and how long these projects will update a library when we know that they are flawed. Not necessarily the primary repositories or the packages updating themselves, but in fact, they have to update and then the developers can come update their code. When we look at the half-life, that is time to close 50% of the libraries. Out of everything with a score of 2, we're seeing about 237 days, if I'm right, and then up at 9 at the you know, quote unquote more secure packages, we're seeing about 168 days to actually update about 50% of the packages with a score of 9. And if you sort of squint, you can see that generally, you know, you put a line across those bars, you might see it sort of go down shorter, if you will. So those with a higher OpenSSF score, whatever the packages are doing, they tend to get updated a little faster than those with a lower score, is all that plot is saying.
But it's also worth pointing out that we see remediation half-life you know, sort of across the board. There are a lot of different factors at play. So for example, just looking at language, we see remediation timeframes in Java, the half-life being 243 days, whereas for JavaScript it's 116 days. So other factors like language selection can completely, you know, not overrule, but it may be a stronger signal even than just the OpenSSF score. So there is something there, but there's a lot of other things that sort of contribute to remediation performance for those upstream applications.
And that language consideration is something important probably throughout every slide in here, that to just talk about application security in general is okay, but to really make it useful, I think you really got to do some language breakout, which we try to do in a lot of our research. And this one, so this is called a survival plot. And so we were talking about that half-life. And so what this plot is showing is on the left, when something is discovered for the first time, that's day 0 basically, and 100% of things are still open. That's in the very upper left. As we go through time, let's say you get 3-4 weeks into something, 6 months into something, what is the probability that that is still open, that the package hasn't been updated? And we see this line sort of drop off, as you would expect. At some point, might get to 0 unless something is left open, but this technique is called survival analysis, and it does account for things that are still open. So you may hear people talk about MTTR, mean time to remediate. Generally, when that's calculated, it just looks at those that have been closed, and you can get some skewed results if you just focused on things that are closed. But this is accounting for things that are closed and still open, and so that's why you get this sort of curve thing. Over time, you're going to have some chance of having things closed, and that's what we're seeing here. So those libraries that have an OpenSSF score, that is the overlap part that we're looking at, we see about 36% open at about a year, 36% chance still being open at a year. And those that do not have an OpenSSF score, that is the outlying part of that small circle, we're seeing about 52% of those at a year still being open. So, and it's sort of interesting to see the difference here. This is a pretty significant difference. Having created a bunch of these plots, it's a pretty significant difference in that remediation time for those with an OpenSSF score and those without. And those without could be for any number of reasons. We have no idea what they actually are. It could be an internal package. It could be something that's not open source, a commercial package, anything like that.
So we've talked a lot about OpenSSF without really getting into the nitty-gritty of it. And so let's show you some of that. These are the kind of the different factors that are measured, and we'll focus on a few of these to kind of say what we're interesting. But a few things that I want to point out. If you can read it, notice the counts for each factor, which is at the top, the n equals value. Now, I mentioned before that there's about 1.2 million libraries in the data set, but they don't all have a score for every single factor here. And so you'll see some of these have a much smaller n number. For example, the packaging one has 23,000, which is much, much smaller, right? A lot of them don't get a score for that factor at all. And the main reason for that, for packaging or for some of these other ones, is that what they're measuring is that you are doing something that they have deemed as good, right? So, for example, with packaging, the fact that you have integrated the project with a known packaging system, right? They'll look for signs of that, and they'll give you a good score if you have it. But they don't want to give you a 0 just because they don't have familiarity with all of the different packaging ecosystems, right? You might be using one that they're just not aware of, or they don't have an ability to measure, and so they're not going to give you a 0 because of that, just because it doesn't know about PyPy or doesn't know about NPM, which are two things that are actually true. But then other checks like SAST, for example, static analysis. Are you running static analysis against your code base? They give you the positive score if you use one of these 3 tools that they recognize. But then you get a 0 otherwise, even if you're using another SAST tool that they just can't detect. So you can see it immediately, there's an inconsistency there, right? On the packaging one, you kind of get the benefit of the doubt, and you only get dinged if you don't get dinged, right? You just get a missing score as opposed to a 0. But in SAST, for example, if there's a limitation to the tool, which there is, they'll just give you a 0. Oh, you're not using one of the 3 SAST tools that we like or that we recognize. The other thing to notice is look how skewed most of these measurements are towards one end or the other when you look at the histograms. And a lot of that can be because what they're measuring is just a yes/no answer. Are you doing this or are you not? And so you see these really tall bars in the 0s or the 10s in some cases. And as we get into some of the charts, you'll kind of see that there are some data points in the middle that are not visible here, but they're just very, very small. And some of them they take, like for example, they look at activity over the past X number of days and count the number of times you did some activity, right? And then they'll normalize it over that 0 to 10. So it's possible to get a 3, 4, or 5. Or there's a rubric that says like, all right, here's 10 things that we think you should be doing in this category, and if you're doing 5 of them, then you get a score of a 5. So there's different ways of measuring and assigning scores to these factors. And some of it is correct in the documentation, some of it's a little bit light on the documentation, and others are, and again, there are sort of inconsistencies around the way that these are calculated. So it's important when you're thinking about using this type of metric to understand where it comes from, how it was calculated, and what its limitations are.
I think we should also take a moment and talk about pulling this data.
Yes.
Because we had something really interesting. They put all of this data for these repositories out on Google Cloud through BigQuery, and they have an API for it. So if you have a specific repository you want to look up, you can look it up. And they've got a nice web interface for it too. If you just want to look up one, just go there, you can look it up. But if you wanted to pull all the data like this, they allow you to do it through BigQuery, but never do that, not until they fix it. Because we did that, and we pulled all the data down, we started working with it, and then last Thursday, Chris sent me a message and said, hey, I looked up a thing in the web interface, but it wasn't in the data. And it was a mismatch. And so BigQuery, we found out, actually dropped a large portion of the data as you're pulling it. And so there's a lot of things missing in BigQuery. So this is in fact current through the API of all of the data in there. So just be cautious if you go through the BigQuery method and you want to look and play with this data. It's all out there. But we recommend going through the API, unfortunately, and pulling down individual packages one by one, all 1.2 million.
Yeah, which takes a little while, but I don't think, Jay can't possibly state strongly enough how much data was missing from BigQuery. Some of these charts, there would be most of the libraries wouldn't have a score for that factor, and when you query the API directly, it's all there.
For example, vulnerability is the last one in the bottom middle there. You can see most of them are 10, which is about, 60% or so. Those were all marked as missing in BigQuery data. So 60% of the repos that are supposed to be 10 were marked as missing, which is not a great start to the analysis we were doing.
Yeah, so a lot of fun with data.
So thank you, RSA people, for allowing us to update the slides. Thanks for that.
We'll talk about a few of these individual factors just to kind of illustrate kind of what's being looked for, what some of the limitations are of those checks, and just sort of a little bit of color on them. We're not going to go through all of them, but just some of the ones we thought were interesting. This one looks for binary artifacts in the repo, so the idea being okay, binary artifacts are a little bit harder to review than source code artifacts. But there's a lot of reasons why you might have binary artifacts in a repo, right? What if you have a compression library and you need to have a unit test for decompressing something? It's a good reason. What if you have stuff in there that you use for building the project that, rather than at runtime? So there are legitimate reasons to have binaries in there. But what this one does, it just subtracts a point from 10 for each binary artifact it finds. If you have 10 or more, then you get a 0 score, and that's how it goes. Most open source projects do not have any binary artifacts, as this shows, and there's a little bit of a distribution there.
The other thing to think about is what exactly is this measuring? What is the bad stuff here? And a binary artifact is going to be essentially the injection of malicious code, right, Chris? I mean, there could be a vulnerability in that, but generally, I think the concern is malicious code that you can't review.
That you have no visibility into, no insight. So, and they've rated this sort of in their weighting system as a high, and so whatever the score here is going to be multiplied by the high impact factor. Code review. This is an interesting one because it looks for a human review of the most recent 30 changes, and there are a few caveats. So the merger has to be different than the committer. There can't be any sort of automatic bot review, so those things are removed. And then they take that score, they normalize it across those 30 change sets, and you get a score between the 0 and 10. So we can see that code review is still relatively rare, right? Only 1.4% of projects get that score of 10, which means that they're getting code review of the most recent 30 changes. If you want to take a positive spin on it, you can say that 18% of applications are doing some level of code review. Obviously, if you have a single developer project, you're going to fail. There's absolutely no way for you to have a different committer than merger. So there are things like that. that you have to understand how to interpret about the score. And also you remember that with code review, reviewed doesn't necessarily mean reviewed for security. It just means it was reviewed. There's this whole, going back many years, this many eyes, fallacy, like open source is going to be so much more secure because there's more eyes on it, but it's not necessarily always the right eyes. They're not always looking for the same types of things that a security reviewer might be. So this is what we see with code review and kind of the limitations to that check.
Yeah.
This is a weird one. We don't really know. We don't really know why the only 12,000 of the repositories get a score for dependency update. In theory, it's a pretty simple check. It looks for whether or not a dependency update tool is configured in the library, in the project. So look for Dependabot and a couple of others. And you get a 10 if it's there. And we talked before about, you shouldn't get dinged if it's not there. But again, 99% of the projects in GitHub that are in this data set are not getting a score at all. And we're not exactly sure why that's happening. And as I was kind of going through this, I was thinking, well, you could really game the system on this one too. Like the check doesn't look at whether the dependency update tools actually run, and it doesn't measure whether you take its advice and accept the pull requests that are generated by the tool. It just looks to see if you have something defined. So if you want to score a 10 on this, just drop a Dependabot YAML file in the repo, and it'll think that you're using a dependency update tool. So again, important to understand how these things are being calculated. I don't think anyone's gaming it necessarily, but like it's easily gameable.
Branch protection. So again, this is looking at introduction of malicious code, I think. I mean, like that's one of the main purposes. Although it could be for code review as well to have branch protection, so you do separate development on branches. But again, you can see 10% is missing, 89% is 0, and very, very few have 1 or above. Just another case where it's 0 or 10, and this is almost all 0, or missing.
Yeah, these things like preventing branch deletion or force push or requiring reviewers for approval, things like that, it seems like not nearly as prevalent as I guess you might think, at least for what you would consider to be a mature project.
Yeah. And when we get to license, again, this is like its own risk. And it's pretty binary. I mean, either something is, has a friendly license, and I think they, in the data they talk about FSF or OSI compatible license. And again, 0 or 10, and there's some at 9. I can't remember why they're 9. I think it was one or the other or something like that.
I think 9 was if you have a license defined, but it doesn't fall within a particular list that they like or something like that. I don't remember either.
Yeah, but the next slide, we actually pulled out the licenses of the 30,000 and looked at what they are. And there's a couple of things to call out here. So like the 10% that we saw on the previous slide might be looking at either the no assertion or the no assertion and those missing. That first one where it says NA means that there was no license file at all. But the no assertion is basically the same thing. And what could happen in those is that the package maintainers could go add a license later, right, and update something in there. But the MIT, Apache 2.0, things like that, those are more friendly license, the FSF or OSI approved. But this is something to keep in mind, to look at these and to think about this moving forward. It's a completely separate risk than, say, a direct security problem.
But it's there.
And so here we're starting to get into the really interesting parts. Again, looking by language. This is looking at activity in the past year, either active or inactive. This is over the past year, a 12-month period. And then contributing developers, either a single developer or 2 or more. And this is something we did a little over a year ago. And JavaScript, you can see, sort of sticks out there as 92% approximately have a single developer and has been inactive for over the past year. These are libraries, these are applications that have at least one of these, right? 25,000 JavaScript applications had libraries in there that had single developer inactive for over a year. Java, I mean, most of these are inactive, So like Java has it in the lower right, so you've got 2 or more developers, but still inactive over a year, 71.5%. Moving on though, we've got maintained, which is the same thing in the OpenSSF scorecard. And what we see is basically 1.1 million of those projects are listed as unmaintained. And I think they've, 90-day is what they say. They will scale, I think, up to 90 days between there, with 10 getting 3.5% getting a 10. Now this is part of the challenge, and this also has a weird scale. This is one of the weird scale, right, Chris, or not?
Yeah, this was the one that like, it's really hard to, like the 0 doesn't mean it's not maintained at all. It means that it has 0 or 1 commits over the past 90 days, which is totally not intuitive, right? 0, you'd think 0 would mean 0.
Right.
But it does, and then like a 10 is like updated at least weekly, something like that.
And they would look at the issues too. So it was like 0 or 1 commits and or issues, activities in the issues or something. So that's what they would consider active. Now if we actually look at the data though, on the next one, this is the actual data. And so you can see on the left, this is over years, this is looking at 3 years. Even at 3 years, there's gets up to 85% or so. So 15% of these repositories have been inactive for more than 3 years. But you can see at the left, there's a lot of activity on the left, so like up to 40%, maybe even up to 50%, but 37% of the libraries are over 90 days without activity. And that's it's slightly different than what we're seeing in the OpenSSF stuff. But if we look at the lifespan of repositories and we look at basically when was this package created, when was the repository created, and when was the last activity, and we look at the difference. Really nice distribution here, right? Nice sort of bell curve, with the exception of that big bar on the left, which is basically someone created a repo, dumped their code in, and they've never visited again. And that's what we're seeing, that big sort of spike on the left. But we do see some projects, the average being about 7 to 8 years active life, up to almost 16 years of life in those. And these are variables that we're going to look in and throw into a model at the end here, by the way. And so vulnerabilities, we talked about this a little bit, and what they do is basically, if you have 0 vulnerabilities, you get a 10. If you have 1, you get a 9, so on and so forth. And if you have 10 or more, you have 0 in there, and then 0.2 are missing.
And this is as reported by the OSV, the Open Source Vulnerabilities Project, which is osv.dev. So they're not like scanning the projects themselves, they're just looking it up and seeing how many known vulnerabilities there are.
Yeah, and I think this looks at the direct code in that package and or its dependencies. And so that if you pull in a package that has vulnerable dependencies, it'll still get dinged for that. And that's why you get 10 or more typically is in that transitive portion. But if we looked at the number of libraries across different languages, how many of these libraries have known vulnerabilities when we look at OSV? And so Java, you can see about 7% of those libraries, .NET about 3%, 4% for JavaScript. But the really interesting part is when you look at an application, which is this slide, and what we see is that the transitive, which is the dark red, this is, you've included a library that itself will bring in something else. We see that, but the direct is the light pink. But together, whether it's direct, transitive, or you've got libraries that are both, we're seeing majority. Over 80% across all 3 languages of these applications have some sort of vulnerability in all of their dependencies.
And it's just a side effect of the hundreds of libraries that are being used to construct these applications. That 7% on the previous slide seemed pretty good, but when you take it as a whole, it's a completely different picture.
So if you think of it like a random chance, if 7% chance of something having a vulnerability, but you're doing that 100 times over, this is a great look at the view. So these are both on log scales, but depending on the language, so if you look at Java, you've got 10, 100, 1,000 direct, and if you have a bunch of direct, the transitive is going to grow proportionally, right? Typically about 10 to 1. And they're different across languages. So JavaScript has a large dependency. When you look at 100 and you go up, a lot of that is basically a little over 1,000. So like a 10 to 1 minimum multiplication for a JavaScript library. So every JavaScript package you bring in, you're probably bringing in another 10 to 12 transitive dependencies for that. Java and .NET are much lower than that. This again, we want to get to the good part here, but we're looking at the transitive to the more direct, and you can see JavaScript on the bottom there, just bringing a lot more of that transitive. You got a lot more libraries being brought in. Let's swap over to diversity, because I think this is where we can start to get some interesting bits. The home stretch, yeah. So this is using a Shannon's diversity index, which for those who know Claude Shannon, the father of information theory, he's also a mathematician and has some contributions like this diversity index, for example. So this is looking at the commits by user, the number of commits. And so you can see these examples in here. So like first look at the chart though, the single developer, you see a single developer, big bar, very low diversity. That is the lowest diversity you can have, one developer doing all the commits. If you have two developers, like in that example where one of them did 29 commits and a second user did 1, still very low diversity. And as you get more developers, like the third one is a pretty good example where like 2 of the people are doing most of the commits, but still you get diversity among those 2, so you're getting a better diversity score. Basically, when you get out in that tail, you have more developers doing more commits. You're spreading the diversity, the commits across a diverse number of developers. So this is something we can look at to say, is this an indicator of problems? So we grabbed all of these variables and we tried to throw them into a model and say what actually is contributing to vulnerabilities. So we had that initial OWASP top 10, we're specifically focusing in on vulnerabilities. And we did a technique called ElasticNet. And what ElasticNet does, it's a way to sort of filter down all of these variables into things that are strong contributors. If you think like it has a little knob on it, and it's going to turn up the resistance, and if there's enough of a signal to get through that resistance, it's going to show up here. So it's interesting, like the first one at the top is the custom one for active development in years. So for every year that a project has been active, they've got a slightly higher chance of having vulnerabilities in it. This isn't a shock. Like if you've got something around for 2 days, much less likely to have than something that's been around 15 years. To be an OSV like that. The next one is super surprising. A security policy, that is a security policy file in the base of the repository. This is an indicator of more vulnerabilities. If you have just the file in there with your security, is it security.txt, I think it is?
Security.md.
MD?
Yeah.
And so if that's in there, basically gives people a way to contact you for security problems, right? And so if you have that in there, it's an indicator that in OSV you're more likely to have vulnerabilities. And that could be for any number of reasons. Again, this is correlation, not causation. But it could be that maybe you take security more seriously and you've got vulnerability disclosure process and you want to put it into the right process. If you don't have it, maybe that project is more likely to just do a quick fix and not go through a disclosure process and just treat it like a bug, not a security problem. SAST and DAST, we'll swap over to this. This is a good one too, because we can talk about the variables here. This is actually looking at the actual contribution. So like we talked about the active development years, it's right in the middle. It is increasing it, but not by a lot. The one that increases it the most is this dependency update tool. No update tool detected. If you don't have one of those, that's a pretty good indicator that you're gonna be in OSV, that you're gonna have a lot of vulnerabilities in there. More than, say, if you did have a dependency update tool, part of it.
But then those next 3, like the security policy we already talked about, those 3 are like specific techniques that basically encourage finding vulnerabilities, right? If you're running a fuzzer, the goal of that is to find vulnerabilities. If you're doing code review for security, you're finding vulnerabilities, and we already talked about security policy. So it makes sense that those 3 are kind of correlated with more vulnerabilities. But SAST tool detected at the bottom there, second from the bottom, that's also intended to find more vulnerabilities, right, in a project. But it has the effect of actually being correlated with less vulnerabilities in the project. So having that sort of practice in your workflow actually has that correlation.
And one of the big takeaways that I hope people take from this is when we look at this, so like the OpenSSF scorecard is intended to talk about risk, and it sort of treats it generically. And there are things that may contribute to risk that are not intuitive. And so like if you're trying to score these manually, you may end up with some weird, incorrect attributes in there. You know, such like the security policy or fuzzing or code review. You know, like these things seem like really good things, but if you want to you know, you're tracking vulnerabilities and you want to go after things with vulnerabilities, in the data, it looks like these are correlated with more vulnerabilities. Not that they're causing it by any stretch, but just when you see that, they are more likely then to cause something downstream where you may have to update them. So they are indicators. They are sort of correlated factors that may cause this in the future, or correlate with it in the future. So the interesting thing about all of this, by the way, is that the data collection here, we relied on OpenSSF for a lot of it. And so we did not go through individual tests that they're doing and say, are they collecting this correctly? The other thing is that there was a lot of noise. You know, as models are built, we can measure the performance and the overall accuracy and things like this, and this model was a little bit lower on that scale. And so there was definitely a lot of noise here. And so what that tells me is that during data collection, there could be noise introduced during data collection, or some of those variables are not helpful. We may not need to look at, like license, for example, did not show up on that list. It did not, when I turned that knob for the resistance, it did not get through that resistance because it doesn't really contribute to vulnerabilities in any way. It was just noise. And so there's a lot of noise in there. And so putting some smarts up front and really getting at the data collection is going to be good. The other thing, the known vulnerabilities, we're specifically going off of OSV. There's a lot of other things you could look at. And the other thing, you could also look for one specifically about malicious code introduction, things like that. So where to go from here? Getting into the OpenSSF scorecard, the source code and the repo, I think this project has a number of issues open in their repo, in the OpenSSF scorecard repo. They've got a number of issues open. I think they could use some help. And hopefully we can talk to them about what we found here too and provide some feedback. But I think that they're purely a volunteer org, and so they might be looking for volunteers to help go through that.
So we'll wrap it up. What should you go do as you're thinking about how to select libraries and what metrics and measurements to use going forward? So we already talked about the challenge in getting the data, and so again, don't use the BigQuery database.
Yeah.
First thing you can do pretty quickly, check out the scorecard, look up some of the libraries that you're using in active development today and see how they score, not just the overall score, but what are those different factors and some of the detail that they'll tell you, like kind of why they scored it that way. And so pay attention to those components. As you go a little bit further out, you know, think about, you know, there are different categories of risk. We talked about vulnerabilities, there's license risk, there's malware risk. Like, what is your organization? What are you optimizing for? What do you care about for most? It's, you know, there's not a super model that's going to capture everything, right? So think about what you're trying to measure there. And then as you go down this path of trying to make it a little bit more scientific, you know, sure, start with some of those individual factor measurements from OpenSSF. It's a good starting point, but you know, you may want to think about different ways to assess those factors, to build the risks that are captured by those measurements into your own scorecard that's more tailored to the risks of your organization, what you're willing to take on, what you're not willing to take on, and sort of those specifics. You want to add anything?
No. And if anybody has any questions, we've been told to instruct people to use the microphones. So if anybody has a question, run up to the microphone, or you can shout it and we can repeat it. But we've been told to recommend the microphone.
Well, we're almost out of time anyway, so
yeah.
thank you all.
Thank you all.